Hello lovelies, in this video we're going to be going through the foundation content that you need for your OCR-Gateway Physics Paper 2. Now this might be the last exam you'll ever sit, which is a pretty amazing feeling really. Well done for making it this far. Now once you've done this, what I want you to do is to have a look at the predicted paper that we've written for this year, have a look at the video walkthrough that we've done to go with that, and then walk into the exam feeling really confident.
We need to make sure that we can describe waves in the following terms. We need to make sure that we know that amplitude is the maximum displacement of a point on a wave from its rest position. The period is the time it takes for a wave to complete one cycle. Wave speed is calculated using wave speed equals frequency times wavelength. Frequency is the number of waves passing a point per second, and wavelength is the distance between a point on one wave and the next point on the same wave. Now, wave speed is the speed at which energy is transferred through a medium. And, as we've seen, we can calculate this using the following equation. Wave speed equals frequency times by wavelength, or V equals F times lambda, where lambda is a Greek symbol used to represent the wavelength. Now, wave speed is measured in meters per second, frequency is measured in hertz, and wavelength is measured in meters. Now, if you're doing physics instead of combined science, we also need to know that when waves travel from one medium to another, the wave speed and the wavelength may change, but the frequency will always stay the same. Waves can be described as oscillations or vibrations about a point. The direction of the vibration can differ, and this is what determines the type of wave. Waves can be transverse or longitudinal, and in a transverse wave, the vibrations are at right angles to the direction in which the waves transfer energy. However, with a longitudinal wave, the vibrations are parallel to the direction in which the waves transfer energy. Now, this can be a bit confusing. If instead we think of it in terms of a long spring like a slinky, and we think, what can we do with this slinky to turn it into a transverse wave or a longitudinal wave? And if we wanted to make a transverse wave, we would want to take that slinky and move it up and down and up and down and up and down. Now, if you think about it, the waves are moving forward, but the vibrations, your hand, are at right angles to that forward direction. Longitudinal waves, on the other hand, if you had that same spring or slinky and you wanted to make a longitudinal wave, you would bump it back and forth with your hand. And there, your vibrations, that movement of your hand, is parallel to the direction in which the waves transfer energy. Now, for ripples on the surface of water and sound waves in air, we need to know that it's not the water or the air that's travelling, it is the wave. So if we think, for example, about a stone that is dropped into water, we can see that ripples are produced. However, neither the water nor the stone move with the ripples. It's just the wave. If we also think about someone speaking, in this case, the voice box will be vibrating, making sound waves that will travel through the air. However, that air is not moving. We need to ensure that we can label a transverse wave and recognise its shape. So the transverse wave, as you can see here, looks like your very typical wave, up and down and up and down. Now, the tops of each of these waves is called the peak, the bottoms are called the trough. The height from the equilibrium position to the peak or the trough is called the amplitude. Make sure that you don't say it's from the peak to the trough, that's a very common mistake. And the wavelength is the distance between two identical points on the wave. Now, an easy way to do this is going from peak to peak or trough to trough. So here, another wavelength that we could draw on would be this position here. It is identical to the wavelength labelled on this diagram, but perhaps it's an easy way to identify it. So some mechanical waves are transverse, for example, water waves and seismic S waves. In addition to this, all of the electromagnetic waves that we will learn about in more detail, for example, ultraviolet and infrared, are all transverse. Now, longitudinal waves look like this. Longitudinal waves have compressions, which are regions of high pressure, where the particles are close together. And they also have rarefactions, which are regions of low pressure, where the particles are far apart. Now we'll find that some mechanical waves are longitudinal. These include sound waves, ultrasound, and also seismic P waves. Waves can get reflected at the boundary between two different materials. When sound waves get reflected, we call this an echo. Now, the law of reflection, and this is important, states that the angle of incidence is equal to the angle of reflection. However, it's really, really important that you know that we measure these angles from the normal, which is this dotted line, as you can see in the diagram, which is at right angles to the surface. A very common mistake would be to measure that angle from the surface instead. So make sure you know the law of reflection and make sure that you can draw on the line of reflection if you know the angle of incidence. Now, when a wave meets a boundary between two different materials, it may behave in some different ways. Some of these ways are reflection, absorption, and transmission. So reflection is when the waves bounce back from the surface. Absorption occurs when the energy of the wave is transferred into energy stores within the material it's travelling into. And finally, transmission is when the waves continue to move into the substance after they cross that boundary. Now, we might be asked how to measure the velocity of sound in air. Now, an experiment that we could do to do this would be to have two people stand a large distance apart, for instance 100 metres, use a trundle wheel to measure that distance between them because it's too large to use the meter rule. Now get one of these people to make a loud noise. So perhaps they could bang together two wooden blocks or bang together some cymbals. And the other person is going to have a stopwatch. And you're going to ask this person to start the stopwatch when they see the person make the noise, and then stop it when they actually hear it. Then we're going to repeat this experiment and take an average, take the mean. We're going to use the following equation now to calculate the speed of sound in air. So we know that wave speed is equal to distance, which could be that 100 metres, and then we divide it by that mean time that we calculated it takes for the person to hear the noise. We could also be asked how to measure the velocity of ripples on water surfaces. So to do this, set up a ripple tank and add water to it to a depth of about 5 centimetres. Now we want to adjust the height of the wooden rod so that it is just touching the surface of the water. Now we're going to turn on the motor and the lamp so that we can observe low frequency waves. Now we want to measure the length of several waves and divide by the number of waves to find the wavelength. This is going to be more accurate than just measuring one wave. Now we want to count the number of waves that pass a point in 10 seconds and divide by 10 to find the frequency. Finally, we can use the equation that wave speed equals frequency times by wavelength to calculate the wave speed. Electromagnetic waves are transverse waves that transfer energy. They form a continuous spectrum, which means that they're just one giant range of waves with varying wavelengths and frequencies. As you can see down here in this diagram, we've got this long wave which goes from radio wave to microwave to infrared to visible light to ultraviolet to X-rays to gamma rays. Now we need to know these in order, okay? Now there's a mnemonic that can help us do this. There's loads of mnemonics actually. I'm going to give you one, but by all means make your own or find one that you really like. I like to use this one, which is that rabbits meet in very ultra expensive gardens. Absolute nonsense, but if it can help place our different electromagnetic waves in order, then that's all I care about. We need to know that the radio waves here have the longest wavelength, the lowest frequency, and the lowest energy of all of these waves. Whereas on the other end of this spectrum, the gamma rays, we have the shortest wavelength, the highest frequency, and the highest energy. So make sure that you learn all of these and you know their properties. you know that they're transverse waves, they transfer energy, and they all travel at the same velocity through a vacuum or air. Electromagnetic waves become more dangerous as the frequency of the wave increases. This table here shows some of the potential dangers that we need to know. So we need to know that microwaves can cause the internal heating of body cells. We need to know that infrared can cause skin burns. Ultraviolet can cause damage to surface cells, leading to skin cancer as well as premature aging. It can also cause damage to the eyes, leading to eye conditions. Now, X-rays can cause mutations and damage to body cells again. And gamma rays can also cause mutations and damage to body cells. Different substances may absorb, transmit, refract, or reflect electromagnetic waves in ways that vary according to the wavelength of those waves. If the electromagnetic wave changes velocity when it moves from one substance to another, it will be refracted, and this changes its direction. As you can see in this diagram here, we might need to use ray diagrams to show refraction. The angle of incidence and the angle of refraction are always measured from the normal, not from the surface. Make sure that you never forget that. That's true for reflection and refraction. We always measure that angle from the normal. Wavefront diagrams can be used to explain refraction in terms of the change of speed that occurs when a wave travels from one medium to another. Wavefronts are simply imaginary lines that are drawn perpendicular to the direction that the wave is travelling. If a wave slows down, you can see that when it crosses that boundary, the wavefronts become closer together. However, if a wave crosses a boundary at an angle, then we notice that one end of the wavefront will change speed before the other, and this is what changes the wave's direction. The atom is made up of 3 different types of particle. So we have protons, which are positively charged particles found within the central nucleus of the atom. Then we also have neutrons, which are also found inside the nucleus of the atom. Neutrons, however, have no charge, and we might see this referred to as being neutral. Now, that third particle found within an atom is the electron. Now, electrons are negatively charged particles, and we don't find them in the nucleus this time. We find them in shells which orbit the nucleus. So you can see all this in our little diagram here. And we have to get very used to these diagrams and being able to label them accurately. We also need to have an idea of how small the atom actually is. Atoms have a radius of about 0.1 nanometers. This is of the order of 1 × 10 to the minus 10 meters, so really tiny. The radius of a nucleus is less than 1/10,000th of that of the whole atom. So the radius of the nucleus is about 1 × 10 to the minus 14 meters. This table here summarises all of the facts that we need to know about the protons, neutrons and electrons. We need to know that the relative charge of a proton is +1, the relative charge of a neutron is 0, and the relative charge of an electron is -1. We also need to know that the relative mass of both the protons and the neutrons, so both particles found within that nucleus, is equal to 1. However, the electron's relative mass is really tiny compared to this. We might see it referred to in several different ways, but essentially, the relative mass of an electron is approximately 1/2000, or we may even sometimes see it referred to as just very small. Now, it's important that we know a few key facts relating to this information. So atoms of different elements will all have different numbers of protons. This is part of what gives them different properties. However, all atoms of a particular element actually have the same number of protons. Now finally, if we have a think about the mass of an atom, we can see that the relative mass of the protons and the neutrons is so much more than that of the electrons. And this is why almost all of the mass of an atom is found within the nucleus. Electrons are arranged at different distances from the nucleus. Now these distances are referred to as energy levels. When the atom absorbs electromagnetic radiation, this can cause the electrons to become excited and move to a higher energy level. The diagram here shows us this. The radiation comes in, and the electron absorbs the radiation and moves to a higher energy level further from the nucleus. If we think about it the other way around though, if the atom was to emit electromagnetic radiation, the electrons may move to a lower energy level again, closer to the nucleus. In chemistry, we will often see isotopes coming up. Now we need to know what is an isotope. Isotopes are atoms of the same element that have the same number of protons but a different number of neutrons. Here you can see I've got two different isotopes of helium. The helium-4 isotope has 2 protons, 2 neutrons and 2 electrons. However, the helium-3 isotope has 2 protons, only 1 neutron and 2 electrons. So notice here, the thing that makes these isotopes of each other is that they still have the same number of protons, however they have a different number of neutrons. Now let's have a think about the ion. What is an ion? An ion is a charged particle which forms when an atom or a molecule gains or loses an electrons. So here I've got a diagram of a beryllium atom. I can see that it has 4 electrons. Now the beryllium atom can lose the 2 electrons within its outer shell to become a beryllium ion. Now because it's lost 2 of these negative electrons, it has become more positive. Think about it like if you lose a negative thought and you become more positive and happy. That's exactly what this beryllium has done. So because it's lost 2 electrons, it now has a 2+ charge. And this is how we would represent this in an exam. Now let's have a look at how the atom is represented on the periodic table. Now the biggest number is known as the mass number. The mass number is very important because it represents the sum of the number of protons and the number of neutrons. Now the smallest number of the two is the atomic number, and the atomic number gives us the number of protons within that atom. So much information given just from this periodic table. So it's important that we know atoms have no overall charge. Now that then leads us on to the fact that in an atom, the number of protons, those positive particles, must be equal to the number of electrons, those negative particles. And that's how they can have no overall charge. Some atomic nuclei are actually unstable. Unstable nuclei will randomly emit radiation to become more stable. Now this is the process of radioactive decay. Now there's different types of radiation emitted from the nucleus. We need to know these 4. We have alpha particles, beta particles, gamma rays and neutrons. Now we need to know a bit more information about the nature of alpha, beta and gamma radiation. Alpha is represented by the Greek symbol alpha. The nature is that it's 2 neutrons and 2 protons, or we might describe it as a helium nucleus. And the change in the nucleus that emitted the alpha particle will be a loss of 2 neutrons and 2 protons to its nucleus. Now let's have a look at beta radiation. Beta radiation is represented by the Greek symbol beta, and its nature is that it's a fast-moving electron ejected from the nucleus. If we think about the change that we see in the nucleus that emitted it, we're going to see a neutron decaying into a proton and an electron, which was, of course, that beta particle. Finally, we have gamma radiation. This is represented by the Greek symbol gamma, and its nature is that it's electromagnetic radiation emitted from the nucleus. The change in the nucleus will be that some energy is transferred away from the nucleus when that gamma ray is emitted. Activity is the rate that an unstable nucleus decays, and we measure activity in becquerels, which is represented with a capital B and a little q. We also need to know about the term count rate. Now, count rate is quite similar to activity. Count rate is the number of decays recorded per second, and we can detect this using a Geiger-Müller tube, like we can see in this diagram here. And we'll see the distinctive clicking sound when radiation is present. And that clicking sound will get more frequent when there is more radiation, a higher activity and count rate. Alpha radiation has a very small penetrating power. It can be stopped by skin or by a sheet of paper. It can also not get very far when it's in air. It can only travel less than 5 centimetres in air. However, it has a high ionising power. Now, for this reason, alpha particles aren't actually that dangerous if they're sat on the table in front of us. Probably they won't be able to travel as far as our bodies, and even if they did, they would be stopped by our skin. However, if we were to swallow them, they would be very dangerous because they would get stopped by all of our internal tissues and cause damage. Beta radiation now can travel further. Its penetrating power is that it is stopped by 3 millimeters of aluminium foil, and it can travel a meter in air. However, its ionizing power is low. Finally, we've got gamma radiation. This is stopped by a thick layer of lead or concrete. It can travel a kilometre in the air. However, its ionizing power is very low. Try and notice here the pattern and the trend as you go down from alpha through to beta, how the penetrating power increases, as does its range in air. However, its ionizing power decreases. We can use nuclear equations to show radioactive decay. We need to know the symbols for alpha and beta radiations to do these equations. Alpha radiation can be represented in 2 ways. Either you can represent it with an alpha particle, with a 4 to the top left and a 2 to the bottom left, or you can have the He for helium, and again a 4 on the top and a 2 at the bottom. Now with beta radiation, we can represent this again in one of 2 ways. Either you can use that Greek symbol for beta with a 0 in the top left and a -1 on the bottom left, or you can do the same numbers but with an E representing that fast moving electron that beta is. Now alpha decay is going to cause both the mass and the charge of the nucleus to change. Because remember, that top number is the mass number and the bottom number is the atomic number, which is the same as the number of protons it has and therefore its charge. So this is what the general equation looks like. You can see that if X has a mass number of A and an atomic number of Z, that number A goes down by 4 and Z goes down by 2. That's to balance it. Now this is easier seen in practice. If we look at this example here, we can see, if we just look at the top numbers, that we've got 226 equals 222 plus 4, and of course that is correct. So we can see that the mass number has decreased by 4. Then on the bottom, the atomic numbers, which represents the charge of these nuclei, we've got 88, and then on the other side we've got 86 plus 2. Now that is balanced, so we can see that the atomic number has decreased and gone from 88 to 86. Now beta decay, because that top number was 0, the mass doesn't change, only the charge of the nucleus due to the bottom number. Now here we can see that the top number has stayed the same, however the Z has decayed to give us Z plus 1. So an example of this is we've got 14 goes to 14 plus 0 along the tops, and on the bottoms though we've got 6 equals 7 minus 1. Don't get confused with the fact that that atomic number goes up during the decay. The reason for this, of course, is that the charge of that electron, that beta particle, is -1, so the charge of the new nucleus has to have increased to balance that. So of course here we've seen that the mass number has stayed the same, but the atomic number has increased by 1. Radioactive decay is a random process. This means that it is impossible to predict which atom will decay next. A term we're going to see used a lot is half-life. Half-life is the amount of time it takes for the number of radioactive nuclei of an isotope in a sample to halve. We could also say that a half-life is the time it takes for the count rate or the activity of a radioactive source to halve. If we look at this example here, we can work out the half-life using this graph, and this is a common question that we get. So looking at this curve, we can see that it starts at 100 grams. Let's halve this then, because we're going to have half the mass once half the nuclei decay. Half of 100 is 50. We read along, hit the curve and go down, and then we read it off the axes. So here we have 4.5 billion years is the half-life of this particular isotope. And we're just going to repeat that method when you're in the exam. Radioactive contamination is the unwanted presence of radioactive atoms on other materials. So an object that is contaminated is radioactive. However, there's a similar word that we can often confuse with contamination, which is irradiation. Irradiation is different though. Irradiation is the process of exposing an object to nuclear radiation. So that we've had exposure, whereas contamination, atoms were present. And an object that is irradiated does not become radioactive. So we need to make sure we know the difference between contamination and irradiation. This table summarises it nicely. So contamination occurs if radioactive atoms get onto a material, whereas irradiation occurs if an object is exposed to nuclear radiation. With contamination, the object is radioactive for as long as the atoms are on it. However, with irradiation, the object has not become radioactive. Finally, contamination is very difficult to remove because we're talking about atoms. However, irradiation, to remove it, we simply need to remove the source or add some shielding. We need to know how we can protect against contamination and irradiation. So we can do this by keeping a distance from the radiation. We might use tongs to handle radioactive substances rather than our hands. We want to limit the time of exposure to the radioactive source, so don't spend too long next to it. And also use shielding. So we can do this by storing our radioactive substances in a lead-lined box or by wearing protective clothing. So we also need to know why it's so important to publish the findings of studies into the effects of radiation on humans. This is to ensure that other scientists can peer review this work. Peer review is very important, and the scientists will check that the research is valid, original, and significant. We need to know about energy stores and systems. A system is an object or a group of objects. We might refer to a closed system, which is a system when energy can't escape or enter the system. So, closed systems are particularly important because in a closed system, the total energy remains constant. However, the energy may be transferred between its stores. So, getting on to energy stores, we need to know the following ones. We need to know about kinetic energy, gravitational potential energy, elastic potential energy, internal or thermal energy, chemical, nuclear, magnetic, and electrostatic energy. So kinetic energy is the energy of a moving object. An example of this is a moving car. Gravitational potential energy is the energy an object has when it's raised above the ground. So an example of something with gravitational potential energy is a book on a shelf. Elastic potential energy is the energy an elastic object, for example a spring, has when it's stretched or compressed. Internal or thermal energy is the total kinetic and potential energies of all the particles within an object. An example of this is a hot cup of tea. Then we've got chemical energy. This is the energy stored in chemical bonds. An example of this is a battery or some food. Nuclear energy is the energy stored in the nucleus of an atom. An example of something that has this nuclear energy is the uranium fuel in a nuclear reactor. Then we've got magnetic energy. This is the energy that a magnetic object has when it is near to a magnetic field. An example of this is a fridge magnet. Then we've got electrostatic energy, and this is the energy that a charged object has when it is held near to another charged object. This can be seen in Van de Graaff generators. Energy can be transferred between different stores using 4 different methods. The first is heating. So energy will be transferred from one object to another if there's a difference in temperature, a temperature gradient, and it will travel from the hottest to the coolest. Radiation is another way we can transfer energy, and in this case the energy is transferred as a wave. An example of this is infrared radiation from the sun. Then we've got electrical work. This is the energy transferred by the flow of charge due to a potential difference. Finally, we have mechanical work. This is the energy transferred due to a force moving an object through a distance or changing its shape. So an example of an energy transfer is a book falling from a shelf. Initially, that book on its shelf had a gravitational energy store. However, that was transferred mechanically by the force of gravity to the kinetic energy store. We need to be able to say different energy transfers dependent on a scenario given to us in an exam. Kinetic energy is the energy of a moving object. So the equation for this is kinetic energy equals half times mass times velocity squared. Or the simple equation of this is EK equals a half mv squared. So the units of kinetic energy is joules, the units of mass is kilograms, and the unit for velocity is meters per second. Elastic potential energy is the energy stored in a stretched spring. The equation for elastic potential energy is equal to 1/2 times spring constant times extension squared. So if we were to do this just using the symbols, that would be E with a little e is equal to 1/2 ke squared, where that little e there is the extension measured in meters. K is the spring constant measured in newtons per meter, and the elastic potential energy is measured in joules. Gravitational potential energy is the energy gained by an object raised above ground level. To calculate the gravitational potential energy, we multiply together the mass with the gravitational field strength and the height. If we do this using symbols, then that's Eg is equal to m times by g, the gravitational field strength, times by the height. Now looking at units, gravitational potential energy is measured in joules, just like all of the energies are. Mass is measured in kilograms. Gravitational field strength is measured in newtons per kilogram. And height is measured in meters. Specific heat capacity is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. We can calculate the change in thermal energy during a change in temperature by using the following equation. The change in thermal energy equals the mass times by the specific heat capacity times by the temperature change. Or if we were to use the symbol equation, this is delta E equals m times c times by delta theta. Now that delta is that little triangle symbol, and whenever we see that in physics, that is telling us that we need the change in that quantity. So we want the change in energy and the change in temperature, which is given by that theta symbol. So in terms of units, the change in thermal energy is measured in joules, the mass is measured in kilograms, the specific heat capacity is measured in joules per kilogram per degrees Celsius, and the temperature change is measured in degrees Celsius. A force does work on an object when the force causes the object to move through a distance. The work done by a force on an object is given by work done equals force times by distance, where work done is measured in joules, force is measured in newtons, and distance is measured in metres. Of course, as always, we could use a little cheeky triangle here if you struggle with the algebra. If not, I would always recommend that you just rearrange this using the algebra that you've learnt in maths, but it's always good to have something up your sleeve in case you get stuck. If you did use a triangle, I would just pop a W on the top for work done and force times distance on the bottom. Now, we need to know that 1 joule is equal to 1 Newton metre. And this is because 1 joule of work is done when a force of 1 Newton causes a displacement of 1 metre. It's also really important that we know that work done against friction will result in a temperature increase. And this is why if you rub your hands together, they start to get warm, because you've done work against friction. Power is the rate at which energy is transferred. We can find the power in one of two ways. The first way we can use is that power equals energy transferred divided by time, or P equals E over T. Now remember, power is measured in watts, energy transferred is measured in joules, and time is measured in seconds. Alternatively, we could say that power equals work done over time. In this case, that's P equals W over T. Power is still measured in watts, time is still measured in seconds, and work done is measured in joules. We should know that an energy transfer of 1 joule per second is the same as a power of 1 watt. And we should also be able to compare different systems. If, for example, I was picking up a box and lifting it up to a certain height, the quicker I do that, the more power I have. The law of conservation of energy states that energy can be transferred usefully, stored, or dissipated, but it cannot be created or destroyed. And this is a really key fact in physics that we will use all the time. So when energy is dissipated, it is transferred to less useful stores. For example, if we have a light bulb, we take that electrical energy store that's inputted and it gets transferred to light energy, which is useful, but also thermal energy as it heats up. Now, this thermal energy is the wasted energy or the dissipated energy. It's important that we know that all energy will eventually be transferred to the thermal store of the surroundings. In the exam, we might be asked how we can reduce unwanted energy transfers. There's 2 examples that they expect you to know. Firstly, we can lubricate it. And secondly, we can add thermal insulation. Those are 2 ways that we can reduce unwanted energy transfers. However, always have a think to the context of the question. For example, lubrication might be useful if we're talking about things rubbing over each other, because that will reduce the friction and therefore that thermal energy transfer that wouldn't be useful. However, I'm sure you can imagine that that wouldn't be useful for every example. So try and always think about the context and think, how can you reduce that unwanted energy transfer? The thermal conductivity of a material tells us how quickly energy is transferred through the material via thermal conduction. The higher the rate of thermal conductivity of a material, the higher the rate of energy transfer by conduction across the material. Now, there's an experiment that you may have carried out which shows this. So the experiment uses dots of wax on different metal rods to compare the thermal conductivity of them. Now, all of these rods, we want to have identical lengths and identical diameters to make sure that any differences in the time it takes to melt this wax will be purely due to the material they're made of and the thermal conductivity of those materials. The rod whose wax will melt first when heated on one end is the one that has the highest thermal conductivity. Houses are designed to minimise heat loss. Houses that have a lot of heat loss are going to cost more money to heat and therefore require more fuel to heat. All of these things are negatives. So the rate of energy transfer through a material, such as a building's roof and its walls, depends upon three things. It depends upon the thermal conductivity of the material, it depends on the thickness of the material, and it depends on the temperature gradient between inside and outside. So when we want to minimise the rate of heat loss when building a house, we want to ensure that we use materials with a low thermal conductivity. This is because those materials are going to have a lower rate of energy transfer by conduction. This means that more of the heat would remain inside the home and not leave the home. Having thicker walls would also decrease the rate of energy transfer because the conduction would have to take place through a greater distance, which means that less heat loss will take place. The energy efficiency of an energy transfer can be calculated using one of two equations. Efficiency is equal to the useful output energy transfer divided by the total input energy transfer. So useful output over the total input. Alternatively, if we're given powers instead, we can say that the efficiency is equal to the useful power output divided by the total power input. So very similar idea. It's that useful output divided by the total input. Now both of these equations as they stand will give our answer as a decimal. Now in the exam you might be asked to give your answer as a decimal or as a percentage. If we needed to get the efficiency as a percentage, all we do is we use these equations, but then we multiply our answer through by 100. If we ever needed to increase the efficiency, we need to increase the amount of useful energy transfer. Therefore, we need to minimise the amount of energy dissipated and wasted. The way that we could do this is things like streamlining, things like lubrication, try and stop frictions within the system, which could of course lead to energy transfers into less useful forms of energy. Frictional forces can cause surfaces to heat up. This can result in an unwanted energy transfer. To reduce this unwanted energy transfer, we can reduce the friction between the two surfaces. We can reduce unwanted energy transfers using lubrication. Speed is a scalar quantity. That means that it does not have a direction. The speed a person can walk or run depends on lots of different factors, such as age, fitness, distance travelled, and terrain. However, unfortunately, we need to know an approximate average speed for certain different activities. We need to know that when walking, the average approximate speed is 1.5 metres per second. When running, the average approximate speed is 3 metres per second. And cycling, the average approximate speed is 6 metres per second. So make sure you learn those key facts. The speed of sound and wind can also change dependent on the conditions. We need to know that the typical speed of sound in air is 300 metres per second. The distance travelled by an object moving at a constant speed for a specific amount of time is given as distance travelled equals speed times time, or S equals V times T. Now, of course, if you're not too confident, you could always turn this into a nice little triangle. This is going to look something like this, where the S is going to be on the top, and then you have V times T on the bottom. So long as you get the marks, I am happy. So remember, distance is measured in metres, velocity is measured in metres per second, and time is measured in seconds. Now, velocity is a vector quantity. Velocity is just the speed in a given direction. Stopping distance is the sum of the thinking distance and the braking distance. So it's the distance in total that it takes for you to stop from the moment you see an object to the moment you stop, okay? So the thinking distance is the distance that the travel thinks during the driver's reaction time. So imagine you're driving along and you see a rabbit run into the road. The thinking distance will be the distance that you travel between the moment you see that rabbit to the moment you put your foot on the brake. And then the braking distance is the distance the vehicle travels under the braking force. So that is the distance you travel from the moment you put your foot on the pedal to the moment you're stationary. So for a given braking force, greater speed is going to cause greater stopping distances. The typical reaction time of a person is between 0.2 seconds and 0.9 seconds. Make sure you learn that fact. Now, there's a few things that can affect the reaction time of a driver, and therefore the thinking distance travelled. The reaction time can get affected by tiredness. The more tired you are, the longer your reaction time, the use of drugs, the use of alcohol, and also the presence of distractions. So for instance, loud music, things like this can distract you and increase the reaction time of the driver. We need to be able to describe a method to measure human reaction times. So here we go, okay? So first up, ask a person to sit at a desk with their hand out. Hold a ruler up to their hand and line up the 0 on the ruler with the person's thumb and forefinger. So now you're going to tell the person that when the ruler gets released, they need to catch it as quickly as possible. So now we're going to drop that ruler, but we're not going to tell the person. And we're going to measure the distance travelled by the ruler in this time before they can stop the ruler. So now we have enough information to calculate the final velocity of the ruler. We can use the equation for constant acceleration that states that v squared equals u squared plus 2as. We know that u is equal to 0 because it started stationary. S is the distance travelled by the ruler that we measured. And a is the acceleration caused due to gravity, which we could use 9.8 metres per second squared or 10 metres per second squared. A question would give you a number to use if you needed it. So now you're going to use that equation to find v, and once you know what v is, you can calculate the time taken using the equation that says that acceleration equals change in velocity over time. Of course, we'll need to rearrange it to get time as the subject. Time would be equal to change in velocity over acceleration. But once we've done that, we can just substitute in the values that we already know to get that time. So once we do that, we will finish off by carrying out some repeats and calculate a mean. To ensure this experiment is calculated correctly and we're actually just working out those human reaction times, we need to make sure that we carry this out in a room with no distractions that's going to affect that reaction time. The braking distance of a vehicle is affected by the road and weather conditions. So if we have poor road and weather conditions, such as icy or wet roads, we're going to increase the braking distance. Braking distance also affects on the vehicle conditions. So if we have poor vehicle conditions, such as worn tyres or worn brakes, again, we're going to increase the braking distance of the vehicle. Now, velocity also affects braking distance. And we need to know very particularly that if velocity doubles, the stopping distance actually increases by a factor of 4. It doesn't just double 2, it increases by a factor of 4, so make sure you know that. Now, when a force gets applied to the brakes of a vehicle, work is done. Now, the friction between the tyres and the brake pads causes the kinetic energy of the vehicle to decrease and the brake pads to increase in temperature. Ultimately, the faster the vehicle travels, the greater the braking force required, and therefore the greater deceleration that we have. Now, of course, we need to know, well, what is dangerous about a greater deceleration? We need to know that the brakes can overheat under these conditions, and the driver may lose control of the vehicle. So make sure you know those dangers. We need to know the difference between renewable energy resources and non-renewable energy resources. So renewable energy resources are energy resources that can be replenished as they're used up. So we can always get more of it, and therefore it's never going to run out. A few examples of these, but we'll look at them more later, include wind, geothermal and solar energy. Let's think about non-renewable energy resources then. This is just the opposite. It's an energy resource that cannot be replenished as it's used up and will eventually run out. So there's a finite amount of that resource available. So some examples of these include fossil fuels, which are oil, coal and natural gas, and nuclear fission. Now, the reason why it's important we say it can't be replenished as it's used up is because in theory we are making more oil, coal and natural gas. However, it takes millions of years. We are not making it at the rate we're using it up, and this is why this is classed as non-renewable. We also need to know what these energy resources can be used for. They can be used for transport, energy generation, and heating. Now let's take a look at those non-renewable resources in a bit more detail. So let's think about those fossil fuels of coal, natural gas and oil to start off with. So some advantages of these is that there is enough available to currently meet the demands. They're also relatively cheap to extract from underground, and they're reliable. We know what we're getting with them. Some disadvantages, however, include the fact that they are a finite resource. They're going to run out. Another disadvantage is that they release carbon dioxide when they're combusted. Now this contributes to the greenhouse effect and global warming. They also release other pollutants, such as sulfur dioxide, which can cause acid rain. And there's a risk of oil spills, which could damage aquatic environments. Now let's have a think about nuclear fission. So with nuclear fission, another advantage is that there is enough available to currently meet demand. Another great thing this time though is that no pollutant gases are released. So there's no sulfur dioxide causing acid rain, there's no carbon dioxide causing the greenhouse effect. It's also reliable. However, some disadvantages of nuclear fission include the fact that nuclear waste that's produced is difficult to safely dispose of, and it needs to be stored for hundreds of years before it can become safe again. Nuclear waste is dangerous. It can lead to mutations, which can cause things such as cancers and other serious conditions. Another disadvantage of nuclear fission is the fact that those nuclear power plants are very expensive to build, to run, and then at the end of their lifetime, decommission. Now let's have a look at the other renewable resources, and we'll look at all of the different ones here. So we've got solar power, which is using the sun. The advantage of this is that it's cheap to run after it's installed in the first place, and it also produces no pollutant gases such as sulfur dioxide or carbon dioxide. However, it's not reliable. We need it to be a sunny day to be able to get energy from the sun. And the initial installation to put those solar panels down is expensive, and it takes a long time to recoup that benefit. Next, we have tidal, which is using the tides in the sea to get energy. Now, this is reliable as there will always be tides. And of course, again, it produces no pollutant gases such as carbon dioxide or sulfur dioxide. It can produce large amounts of energy, which is a great advantage, and there are no fuel costs involved. However, there are of course some disadvantages. When we install the equipment needed to harness this tidal energy, we can damage marine habitats. This installation is expensive, and an issue is that we can't control the supply. We're dependent on the time of the month, according to the tides. We can't say, oh, we need a lot of energy now, so let's turn it up a bit. No, we can't do this, unfortunately. We're unable to control that supply and get more when we need more. We're limited by the tides according to the time of the month. Now we've got hydroelectric energy. So these use hydroelectric dams. Once these are installed, they're cheap to run and there are no fuel costs. And they're reliable, and we can control the energy supply dependent on demand. However, there are again some disadvantages. When we build this hydroelectric dam initially, it costs a lot of money and is very expensive. We will also destroy some habitats when we set this up, which can be a big problem. Wave energy is another source of energy that uses waves to generate it. This is cheap to run, there are no fuel costs, and no pollutant gases like sulfur dioxide or carbon dioxide are formed. However, this can again damage marine habitats, and the installation is initially very expensive. Another issue is that we're unable to control supply. It depends upon the weather because we have bigger, stronger waves in certain weather conditions compared to others. Now, very similarly, we're on to wind power. So wind, again, is cheap to run, there are no fuel costs, and no pollutant gases are released. However, we have certain problems. Wind turbines are very noisy, so noise pollution is an issue. We're also unable to control supply, as just like the wave energy, it's weather dependent. Another disadvantage of wind energy is the fact that for large-scale demand, we're going to need a lot of wind turbines, and therefore we're going to need a lot of land that could be used for other things. Next, we've got geothermal energy. This is again cheap to run, there are no fuel costs, and it produces no pollutant gases. However, installation is very expensive, and there are limited locations that we can set this up. Finally, we have biofuels. Now, biofuels are reliable because the supply can be controlled dependent on demand. So when there's a high demand, we can make more. They can also be carbon neutral because as you grow the plants needed for biofuels, they're going to take in carbon dioxide using photosynthesis, and then when they're combusted, they will release it back into the atmosphere. So they are carbon neutral. However, some disadvantages of biofuels is the fact that they can lead to deforestation and they are expensive to produce. So make sure that you can say some advantages and disadvantages of all of these different renewable and non-renewable resources. The national grid is a system of cables and transformers linking power stations to homes and factories to transfer electrical power. We're going to find two different types of transformer within the national grid. We're going to find step-up transformers and step-down transformers. Step-up transformers are found between power stations and transmission cables. Step-up transformers are really important. They're designed to increase the potential difference and therefore decrease the current. Now, this ensures less energy gets lost through the heating of those cables. This increases efficiency. So more of that electrical energy is transferred from those power stations to the homes and the factories they're going to. Now, step-down transformers, on the other hand, are found between transmission cables and homes and factories. Now, step-down transformers decrease the potential difference to a lower and a safer value. It would be incredibly dangerous if we had potential differences as high as they were due to that step-up transformer entering our homes. The risk of electric shocks and fires would be very, very high. So we use step-down transformers, decrease that potential difference, and reduce those risks. So mains electricity, which we have in all of our plug sockets, is an alternating current supply. Now, what this means is that the current is repeatedly changing direction, and AC current is produced by an alternating potential difference. However, on the other hand, batteries that we use to put into our remote controls, for instance, or have in our phones or our laptops, they provide a direct current. Now, in a DC supply, the current flows in only one direction, and it's produced by a direct potential difference. At GCSE, we need to know a bit more information about our mains electricity supply. So, of course, we know it's an alternating current supply, or AC. However, we also need to know that it has a frequency of 50 Hz and a potential difference of 230 volts. In the United Kingdom, most of the electrical appliances are connected to the main supply using a 3-core cable. Now, this is a really safe system, so we're very lucky to have it in this country. Now, these 3 different wires in the 3-core cable are colour-coded, And this is so useful because it means we can easily identify them and keep ourselves safe. So the live wire is brown, the earth wire is made up of green and yellow stripes, and the neutral wire is blue. Now, as well as knowing the colour of these different types of wires, we also need to know the role that they play and what potential difference goes through them. So the live wire is the most dangerous wire. It carries the alternating potential difference from the main supply. So it carries a voltage of 230 volts. Now the earth wire, which is made up of green and yellow stripes, is the safety wire. And this is very important because it prevents the appliance from becoming live. Now the only time that the earth wire will ever carry a current is if there's a fault in that appliance. But again, the purpose will be to keep it safe. So the potential difference normally then going through that earth wire is 0 volts. Finally, our neutral wire that's blue in colour, this is here to complete the circuit, and this has a potential difference of 0 volts. Now let's have a look at some other key features to the plug. So we can see here that we have a fuse in this plug. Why do we have these fuses? Well, the reason for this is that if the current gets too high, a thin wire inside that fuse will melt. And the importance of this is by melting, this is going to break the circuit. Now, of course, we know that when we break the circuit, electricity is no longer flowing, and this prevents the risk of electrocution, so it makes it much safer. Now, we can also see here we have a cable grip. Now, the importance of this is it holds the wires in place. Now, we'll see that the cable grip, as well as other parts of the wire, such as the flex and the actual plastic casing, is made of the material of plastic. Now the reason why we use plastic is because it is a good insulator. However, the wires are made up of copper and they're coated in plastic. Now the reason why we use copper in the actual wires is because copper is a good conductor of electricity. We need to know why a live wire might be dangerous even when the switch is open. And this is a really important question because, of course, if the switch is open, you might think that the current can't flow. However, if we were to touch the live wire, we could ourselves complete the circuit. And this is because we are, of course, in contact with the ground. And so that current will flow through our bodies into the ground. And so we could be electrocuted. And that's why that live wire is always dangerous, even when the switch is open. We also need to know what the danger is of connecting the live wire to the earth wire. Now, this is a very similar answer to what we just said. If the live wire came into contact with the earth wire, the circuit would be completed, and this increases the risk of electrocution or fires. So you can see there's so many important safety rules that we need to know when using plugs. However, they are designed to keep us as safe as possible.
Ouch! This is why in some videos I'll explain scratches.